it's a pleasure to be here and represent Gas Infrastructure Europe. I'm working for Gas Infrastructure Europe in various working groups. We have storage working groups and also on hydrogen, where I'm chairing the hydrogen regulation task force. My day-to-day job is not for Gas Infrastructure Europe. It's for Uniper Energy Storage.
Excuse me, Michael. Could you please enlarge your screen?
Yes. Is it better now?
Yes, thank you.
Okay. So my day-to-day job, I'm working for Uniper Energy Storage. We are also a member of Gas Infrastructure Europe. We are a storage operator in Germany, the largest one. We have storage sites also in UK and in Austria. And as you can see here, Gas Infrastructure Europe represents the interests of the storage operators. We are around 30 storage operators in Europe, transmission system operators, and LNG operators. I think what is also important in context of Gas Infrastructure Europe, and when we look on the European perspective, is that this decarbonization, we have to consider that it follows different national and regional pathways. So today we are talking about hydrogen and how to develop hydrogen infrastructure and hydrogen storages. But when we discuss these decarbonization activities, I think we have to consider that there are different pathways for some countries. Biomethane, for example, is very important, like Denmark. For other countries, decarbonization will follow more the way of blending hydrogen to the network. And some countries, and I think that's the case also for Germany, have a strong focus on hydrogen and how to set up a hydrogen infrastructure. But on the European level, I think it is also important that the starting point of the transition is quite different, and that needs to be considered. When we talk more in detail on storage, I think it's also important to know that we have currently quite interesting and challenging developments in the storage market. You are all aware that since last year we have to consider the security of supply topic with a lot of new regulations that have been introduced. So not only on the European level, new storage-related regulation with filling requirements have been introduced. Also on the national level, Germany introduced storage filling law obligations with filling requirements. Also with regulatory interventions, how to use storages. For example, use it or lose it principle was introduced. And also other provisions where it is we need for closing a storage site, for example, also the permission of Bundesnetzagentur. So since last year, we have a very strong regulatory interventions in context of security of supply. These legal requirements end according to the law in 2025. Currently, it is discussed also in the German energy law to extend these legal requirements. And that is something which also brings some insecurity in the market, because it's quite, at the moment, not quite clear how long these security of supply related measures will stay. And that has also an impact on the question on scaling up storages, hydrogen storages. Because we have to consider that in the long run, that's following also the decreasing of the gas demand, less flexibility will be needed in the gas market, maybe not for the next 2, 3, 5 years, but if we look 10 years ahead, we have to consider that with less gas demand, and member states are also obliged to reduce their gas demand every year by 15%, which means that in the long run, also less flexibility is needed for the natural gas market. And that has a big influence also on the question on what does that mean in context of repurposing, in new investments? Because on the other side, with the decrease in gas demand and less flexibility for gas storage in the long run, we see a huge increase in hydrogen storage demand. And that is a conflict at the moment, which I think has also an impact on the question of repurposing on investments in hydrogen storage. And what we also have to consider are additional decarbonization costs, which in context of reduction of methane emissions, where we are very active, that at our sites we are monitoring, we are further decreasing our methane emissions, which are very low, but a lot of efforts have to be taken also because of the changing legal requirements. And blending of hydrogen also means that we have to adapt our sites and could lead to additional costs. So that are some developments we see in the coming years that also influence the question how to realize an hydrogen infrastructure, what is the investment framework, and that's a very difficult situation at the moment because the legal framework is not there, and the investments have to be taken now in the next years that the demand for hydrogen storage can be covered. When we look on the European, and I'm sure that we will see that also more from the German perspective, but when we look on the underground storages capacities on the European level, we have more than 1,000 terawatt hours storage capacity, working gas volume in depleted fields, aquifers, and salt caverns. So that are the storage capacities, which is around 25% of the gas demand in Europe. When we look on the share of the salt caverns, so you see here on the left side a number of around 175 terawatt hours working gas volumes in salt caverns, which is a huge figure. And I think what is very interesting in context of Germany is that 80% of these European cavern capacities are located in Germany, I think, which is a very important aspect also in context of repurposing existing sites. So Germany has a share of 80% of the European salt cavern capacities in the moment. And because of the different energy content, different pressure situation, if you would convert all these existing cavern capacities, you would end up with a working gas volume for hydrogen of around 50 terawatt hours to store hydrogen because of the lower energy content and the different pressure situation. If we look on, and we only look on the PCI list of planned cavern projects, we currently see till 2030 around 30 terawatt hours. And I think that is the big challenge now, because on the right side, you see here different scenarios for hydrogen storage demand. I think all these numbers are false, I would say. But you see at the end that all these projections, and we are also currently working in GSE on a study where we want to assess this gap. What is the capacities realistically to be available in 2030, and what will be the hydrogen storage demand in 2030, 2050? I think here you can see some projections, but if you would take the conservative scenario, you would see that we have a much higher hydrogen storage demand than we have available pilot projects. And also if we would repurpose in theory, but I think we need these storage capacities also for the gas market, but in theory, if we would repurpose all existing caverns. So there's a huge gap. So we need new investments. And when we need these capacities in 2030, the investment decisions have to be taken now in the next 1-2 years, that these capacities are there. I think that's more the European picture. It is not so different from the German perspective. I think it's very similar, but I think that's the big challenge. I think that's not new. There are 3 different ways in setting up a hydrogen infrastructure. I think it's retrofitting, where we would blend natural hydrogen into the gas infrastructure, into the storage. With deep blending, I think that could be a quick way in decarbonization, which also have huge impacts on storages, because our investigations show that if we would blend more than 2% in our storages, we would have huge investments to adapt our sites. The other way is repurposing, so using existing transport or storage infrastructure and repurpose that to 100% hydrogen use. We have, as HYPOS energy storage, one pilot project in Caverns. It's a Caverns storage, where we are currently doing this in a project, but we are also testing in our beer bank storage. That's a porous rock storage site in Bavaria, where we are testing and investigating different blending rates in our porous rock storage site. So that we are doing as industry, and also the other storage operators are here testing and running different pilot projects. And as you have seen in the last slide, also building new infrastructure is a very important topic. Hydrogen storages are providing different benefits. I think the benefits, the arbitrage value, so to have here an instrument against the price volatility, I think that these values you already, or most of you are aware for gas storages on the gas market. But this is also a value which we see for the hydrogen storages. Also the system value, so to avoid overinvestment in the transportation infrastructure, storages can play here a very important role. Also in context of security of supply, that's the insurance value, which is very well known also in context of a supply disruption. But what is quite new in the values for hydrogen storage is the kickstart value and the environmental value. So that means the kickstart value, we could so hydrogen storages could also avoid overinvestments in the renewable electricity capacities, and the environmental value, we could avoid electricity generated from gas or fossil-based generation, and provide the flexibility that is needed in electrolyzers for producing green hydrogen. And I think that are 2 additional values hydrogen storage are contributing to the value chain. If you are interested in all the activities and pilot projects on the European level, GIE, and together with other organizations, NZOC has provided an hydrogen infrastructure map. You see here also the link where you can assess here the different projects. So it's on transmission, distribution, storage, where you can see all the pilot projects. At the moment, there are more than 500 hydrogen projects in Europe, which is a huge number. You see here the transmission projects, but you see also that we have more than 50 hydrogen storage projects, which are not only hydrogen Caverns projects, but also porous rock projects, which is also a quite huge number. And I'm sure that we have in this session today also a good overview of what's going on in Germany. So that's quite interesting, and you find also the technical characteristics of these pilot projects on this infrastructure map. I think what is also very important, and I mentioned that before, to take the investments, we need a regulatory and a legal framework for investing, for developing hydrogen infrastructure. So currently on the European level, there is an European hydrogen and decarbonized gas package under preparation. It's currently in the trilogue procedure. That means that the Parliament, the Commission have to, and the Council have to find a compromise. So it's far advanced. But I think that legal framework is then the basis also to adapt the national legislation in Germany, Energiewirtschaftsgesetz, which is very important in context of having a clear market environment, a market design to take the necessary investments. And I think also the timing is essential. We have already, you have already seen that picture. So if we really want to meet the demand that is projected, we have to consider that for repurposing, we need between 3 and 5 years, depends on the project. For new investments, we are talking about more than 10 years. And yeah, to make that happen in 2030, you would have to take the investment decision in 24, 25. And that, I think, is the very important point to underline, that we need this legal and regulatory environment also to take the investment decision, that the capacities can be prepared till 2030. I think that's my last point. That is, I think, the main topics we see also in the regulatory environment is on the, when we talk about the European level, this legislative framework needs to respect different pathways, because you cannot compare the situation in Spain with Romania. I think that is something that the legal framework needs to consider. What is very important is to use the synergies between the existing gas and hydrogen infrastructure, especially in context of storage. We need the storages in the coming years for security of supply. On the other side, we want to repurpose existing storages into hydrogen, and that needs a coordinated transformation, considering also the declining gas demand and the flexibility need. We need a market design with access rules, with tariff rules, where we have to build up a market. So we need a market-based price mechanism. And that is very important also for the operators to take the necessary investments. And we need a coordinated planning procedures, because the big question is how many storage capacities we need in the coming years, where are the right locations, also to bring that together with the European level, the hydrogen backbone, on the national level, the Wasserstoffkernnetz, where are the right locations for storages, where flexibility is needed, and that needs a more coordinated way of infrastructure planning. So that, I think, are the main elements we would see that have to be considered in a legal environment. Yeah, and now I'm at the end of my presentation, and if there are any questions, I'm happy to answer.
Thank you very much, Michael, especially for highlighting what needs to be done to fulfill this goal, for more and more hydrogen storage facilities. One question from my side. You've shown a map with where most natural gas caverns are at the moment. That is in northwest Germany and the Netherlands. When we are converting that to hydrogen, do you need other necessary locations in Europe that has to be converted to hydrogen to stabilize the European backbone grid?
I think that what you can see here is also the framework for the European hydrogen backbone, but you have also national activities. In Germany, it's the Kernnetz, which is the pathway how to develop an infrastructure. And those planning procedures are at the moment ongoing in also other countries. Maybe not so far advanced as in northwest Germany and to the Dutch border. But this is, I think, something which I mentioned before. That's a little bit the problem at the moment, that this is not done in a very coordinated way. Yeah? We have plans on the network, but you need in a hydrogen network, you need also the flexibility. Especially when you want to develop that in the most cost-efficient way and avoid over-investments, you have to look on where is the flexibility need, where are the customers, where are industrial customers, and that I think has to be done in a more coordinated way, which is not the case at the moment.
I do have two questions for you. Is the capacity calculation only referring to gas cavern storage, or does it also include crude oil caverns as well?
No, that was only referred to the gas caverns.
All right. And another question, given the high topside investments for blending of substantial volumes, is blending a sensible option to all at all for storage?
No, because that's what I mentioned before. That blending would cause, if we have blending rates more than 2%, 5%, 10%, I think we would have huge investments. And I think that could lead to a more inefficient market situation as to repurpose into 100% hydrogen storage. But it could be, and that's what I also say, that in some countries where you have not the availability of hydrogen, it could be an option. When I'm talking maybe on Eastern European countries, yeah, it could be an option how to decarbonize the system. And therefore, I think if we see it on the European level, there might be some countries, some national pathways where that could be a pathway. Yeah? But you have to consider that you are faced with enormous costs to adapt the existing infrastructure.
Now we've heard about the big picture from Michael Schmölzer, Gas Infrastructure Europe. Thank you very much for that. But I want to emphasize why we are meeting here today and why the following speaker and companies are presenting what they've done so far. Here in central Germany, we have the so-called Energiepark Bad Lauchstädt, pretty hard German name. But what we are doing here is we are converting 1 out of 17 salt caverns to hydrogen storage. And that energy park means it's a whole concept of a 40 megawatt wind park, wind power plant that is being erected at the moment. A 30 megawatt electrolysis is ordered, and that the volume of that salt cavern we will talk about. We will talk about has 27 million cubic meters. We are also building a 25-kilometer pipeline to connect that storage facility to a chemical park. And the main customer will be a refinery from Total Energies. Overall, it's a huge investment of 210 million euros, and we plan to bring that into operation by the end of 2025. It seems, if I read these facts, it looks pretty easy, but actually it was more than a 10-year journey to get there. At the picture on on the right-hand side, that was taken 3 months ago, and you can see the 2 governors of 2 German states that are bordering that salt cavern. So you can see that, yeah, it's pretty important for high politicians. They see the value of that. There's a lot of funding going into this project, a lot of federal and state funding going into that project, and it's pretty unique and one of the first of its kind in Europe. And as I said, it was a 10-year journey to get here, and we have companies that, or speaker that will start now presenting every little aspect of what they did within the last 10 years to get to this point today. And we will start with Hagen Bültemeyer from the DBI Gas- und Umwelttechnik GmbH, and he will tell us what the design considerations of a hydrogen cavern in general mean, and how that all happened in the energy park I just mentioned. Hagen, please.
So Vega, thanks a lot for this kind introduction, and let's go for it. First of all, I'd like to give a quick introduction to our company as a whole. It was mentioned DBI Gas- und Umwelttechnik GmbH, German word meaning loosely Gas and Environmental Technologies Limited. We are small and medium-sized enterprises located at 2 locations in the state of Saxony in Germany, and we are doing basically everything around the engineering and consulting business for gaseous energy supply. And also we have also a very strong foothold in research and development, and in particular also in the underground world, which is the department I'm the head of. And in this department of gas production, gas storage, we are dealing with all the subsurface aspect. We are not just only dealing with natural gas and hydrogen, but also have different other things in our portfolio, like the classical E&P business, geothermal energy, but the balance shifted very heavily towards the renewable side in the last years. And we consider the underground storages in this new renewable world just in the center of the energy supply, because they serve the purpose of balancing supply and demand. So, and I think one very significant strength of our company is that we are able to consider the entire value chain. So we're not just dealing with subsurface, but also with pipeline transportation, the production side, whether it's natural gas from deposits, reservoirs, or hydrogen from sources like electrolysis or others. And then we can also think about the utilization of our gaseous products and the related quality demands. Okay, but now let's get into the actual presentation. And I want to cover the storage capacities when it comes to hydrogen storage, the pressure development in caverns and wells, stress evaluation, what does it mean for cavern completions or completion of wellbores, and last not least, talk about H2 purity requirements. Okay, storage capacities, first part. Mr. Schmölzer has given you the general picture for Europe. I would like to zoom in a bit more on the German side here, which covers or which provides the largest storage capacities in the European Union at 46 sites. Contrary to Europe as a whole, the majority of storage capacities in Germany are in caverns, because Germany has the advantage of having those very vast salt bodies, in particular in the northern part, more or less here, where you also see all of those little dots in this figure on the right-hand side. So In the currently existing natural gas world, we have a storage capacity of approximately 255 terawatt hours. If we would convert all of the currently existing storages, caverns and pores, we would end up with only 51 terawatt hours of hydrogen storage. And let's come to the next slide to answer the question, why is that? Why do we have such a significant difference between hydrogen and natural gas storage capacity in terms of energy? First of all, when we design a cavern, we need to know how much storage capacity we actually want. And this brings us to the geological conditions, the depths of our cavern, and the related pressure and temperature. As a starting point here, we can use the simple general gas equation, including Z factor, of course, as a component property. And we need to know our cavern temperature and our cavern pressures, which are determined by stress tests in laboratory, and they are more or less deriving from the depths of the cavern itself. And then we can convert our cavern volume that we want to have to the storage volume in norm cubic meters, or vice versa, depending on how you look at it. When we make this calculation with our maximum pressure, we are getting our total gas volume. If we do this calculation for our minimum pressure, we are getting our Cashion gas volume. And the difference between the two is our actual working gas volume, WGV, the number with which we can actually work, and which is our storage capacity. Of course, to do such a calculation, you need to know quite a lot about your storage formation and the actual geological conditions there. If you have only rough numbers for the working gas volume at hand, which are publicly known, also for Europe, you can make a rough estimation for conversion of a natural gas working gas volume to hydrogen working gas volume by just making this calculation with the quotient of the different Z factors. Yeah, the calculation on the left-hand side you can do for natural gas and for hydrogen, and then you will see a difference in storage capacity in volume. And the second aspect is, of course, the energy behind that. Each volume of a natural gas has a higher heating value than the respective volume of hydrogen, and this brings us to the vast difference in energy. As a rule of thumb, you can remember that volumetrically, under the same storage conditions, pressure, temperature, volume of the cavern, you store approximately 1.5 less times hydrogen compared to natural gas. And when it comes to energy, again, 5 times less hydrogen than under the same condition as natural gas. Okay, to put this into perspective, again, some numbers for Germany. The Federal Ministry for Economics and Climate published their so-called long-term scenarios, currently already in the third version, which sums up 3 different scenarios for the development of the storage capacities for hydrogen. And depending on scenario, we are looking at required storage capacities of hydrogen between 47 and 73 terawatt hours. Again, numbers for Germany, by 2045. If we now make the previously shown calculations for Germany, for the porous UGS facilities and the cavern UGS facilities, we are ending up with an, of course, different volume in terms of hydrogen working gas volume that is available, but also a significant reduction in terms of energy of that working gas volume. In fact, we would only end up with 49 terawatt hours, all existing UGS facilities in Germany combined. And this brings us to the very simple bottom line. Our energy transitions requires additional hydrogen underground storage facilities. And in the same way, you can make such calculations for Germany as a whole, of course. Okay, pressure development in the well. When we store hydrogen, not just only our storage volume change, but also our pressure, and that means the stress in our wellbore changes, because those calculations and those physics, they are component dependent. The Z factor I mentioned also earlier, but also things like relative density, they are part of those equations. You can do this calculations for static conditions when the cavern is just shut in. Bottom hole pressure as a function of wellhead pressure and hydrostatic column, but also when we are injecting, respectively withdrawing gas, we have a similar equation, but now extended to our friction losses, which is the dynamic part here. And here again, we are having parts like static column again, Z factor, average temperature, and of course our geometrical dimension, the wellbore diameter. And bottom line is basically the red line here shows the relation between wellhead pressures and bottom hole pressure for natural gas. And you can see in comparison to that, the line drawn for hydrogen is a generic example, but general picture is the same for every site. At the same bottom hole pressure, let's take, for example, 100 bars, we have a higher wellhead pressure in case of hydrogen storage compared to a natural gas storage, because our hydrostatic column is lower for hydrogen because the gas is less dense. And this means our overall pressure and stress in the wellbore increases given the same bottom hole pressure. So if we say our bottom hole pressure in the hydrogen system for hydrogen storage shall be the same as it was previously for natural gas, our wellhead pressure increases, meaning also our required injection pressure for our compressor outlet pressure increases. If we cannot cover such a higher wellhead pressure, then we have their limitation, and this means our maximum achievable bottom hole pressure for our hydrogen UGS facility decreases, which means a further reduction in our achievable working gas volume. Yeah. And here on this chart, I plotted also for a generic example the development of required pressure, discharge pressure, and also not discharge pressure, but pressure power requirement and a cooling requirement depending on hydrogen blend into natural gas. And we can see a significant increase in power requirement when we are blending up to, let's say, 25%, and then we have a steady decrease. This has different physical and component properties reasons, and we can go more into details of that if you like to discuss that in the aftermath. Stress evaluation in the well, also arriving from a different pressure situation. We have basically two different systems there. We have our tubing of our well with our annulus and then our last cemented casing. And we have our system of, let's say, the outside, the casing, the cement, and the surrounding rock. Stress could be either isotropic or anisotropic, and we have then our different inner and outer loads, and also different inner temperatures and formation temperatures from the outside. Can be either isotropic or anisotropic. And then with the different loads that we have from the stress and the strengths of our cement and the formation pressure from our surrounding rock formation, we can calculate the stresses in the wellbore, which is 3D numerical simulation. All of those different equations are behind it, radial stresses, tangential stresses, axial stresses, all of them are combined into this equivalent stress calculation according to Miset. And then we need to see where we end up with our safety factor. Yeah, and our actual resulting stress divided by our equivalent stress should still provide us a certain safety. A factor of 1.25 is common in the gas storage world, which you can also find in various existing rules. Okay. Yeah, here just some example depicted how stress develops from the zero axis of the wellbore to the further into the rock with some examples. And yeah, these calculations you have to do for the natural gas, but you have to redo it for the hydrogen system as well. And this brings us now to our wellbore completion schemes, and you will hear more in depth about that later on as well. But for this general picture, when we are talking about a wellbore completion, we are always talking about two barrier systems, a primary and a secondary barrier, which serve the purpose to control our gas flux, respectively our shut-in. Primary barrier is directly in contact with our storage medium, here blue marked, and it shall prevent uncontrolled influx of our stored gas into our well, just unless we want that to happen when we withdraw or inject. In case our primary barrier fails, we still have a secondary barrier that acts as a backup and shall provide tightness and safety in case a primary barrier is not working or fails. And if the primary barrier fails, we can then still have an tightness and safety, and gives us the required window of time to do an workover of our well. Okay. You also see here that the below our production packer, our last cemented casing is here the only barrier, and this part of the last cemented casing is also in contact with hydrogen, but last cemented casing is difficult to replace, and I will come back to that in the next slide. When we talk about cavern completions, we would also go in the hydrogen world for a classical gas completion with a production packer and an SSV, but just using hydrogen-ready materials, and we are dimensioning it according to our required flow rate and rates and whatnot. However, if we have an existing well, we would still need to deal with the question, what if our last cemented casing shoe would not be fit for the hydrogen world, since it would be in contact with hydrogen? And here we could find a quick workaround with protecting the initially existing last cemented casing shoe with a new protective inner liner, but then again it would reduce our tubing for our would reduce our tubing diameter, and this could result in less or lower flow rates that can be provided. Okay, this slide, I mean, the presentations you will receive in the aftermath anyways, it will be shared, and here I just compiled various steel grades from API and also other norms with their respective yield strengths, tensile strengths, and H2 tolerances, so that you can double check for yourself what could be a suitable replacement for what you actually have installed maybe right now. Okay. And this brings us to the last part, H2 purity requirements. In the last presentations, you will hear very detailed information about that. But when we have a cavern, we also inevitably have a cavern sump. When we generate or build new caverns, normally we don't have any carbon sources or microbiology in those salt formations. However, they could still be possible to bring in due to the leaching water. And difficult is the system always when carbon sources get into the mix as well. Yes?
You have 3 minutes left.
That's okay. Thanks. Fits. And when we are converting previously for natural gas used caverns, we need to deal with the issue if we have still remaining parts of hydrocarbons in there. Was a previously used blanket heavy oil like diesel or something? And this could be a possible hydrocarbon sources. And then we could have various processes going on. Most dangerous, of course, formation of H2S. And yeah, and those processes could be triggered to microbial activity. In the end, whatever happens in our cavern, at the withdrawal site, we would need to deal with the gas treatment. And in general, there are different quality requirements in current discussion. Grades varying from quality grade A to quality grade D, which have an pretty significant difference in terms of quality. Yeah, and this brings us then to the treatment means necessary. I provided here again a lot of numbers from the different norms that also are under development right now, and what is specified there, what is needed for the removal or possible remaining associated components. But now we need to deal with the questions how to achieve those purity grades. And here we have different technologies available, adsorption types, catalytic conversions, liquefations, absorptions, membrane processes. And here I plotted you the different components that can be treated with isamine, with either system, and the current available technical readiness level. Technical readiness level 9 means fit for actual operation. And you can easily see that the adsorption systems, they are most flexible, most versatile, and are basically right now, as per state of the art today, are the prime choice for treatment of hydrogen. Okay, and now where does this lead to? All of the different works here. It leads us to our actual real lab projects. I'm done in a couple of seconds. And just a cover slide from the Real Labor in the Energy Park Bad Lauchstädt. Here also timeline, 10 years story since making all of the projects, fundamental research at the beginning, and then going into the actual construction of that energy park, surface and subsurface. And here again, some key figures just for the subsurface part of this project alone. Okay, with that being said, I'm done. I think it was a quite fast ride through the entire hydrogen underground storage world as an overview. I leave you my contacts here. Feel free to reach out to me if you have any questions.
Thank you very much. Yes, that gave a great overview what all has to be set up before actually starting the construction. We do have a question from another Hagen Paul Niemann, please.
Yes, thank you. Well, thank you, Hagen, for this academic deep dive and great reminder on all the gas properties and so on. So my question would be, you mentioned that there are special alloys to be used for the casing string. And is there a long-term integrity testing conducted for those casings? Or alloys, let's say.
We did a lot of material testing in the HYPOS projects prior to the actual Real Labor. It was done in the H2UGS program, and this presentation from Fraunhofer, I guess, will cover it. The different steels had been extensively tested in lab trials. And now we are at the moment when we say, okay, further knowledge is basically not gainable just by laboratory investigations. Now we need to go into the field and make our experiences there. Yeah.
Okay, thanks. Talking about the field, could you go back to your well integrity schematic, where you presented to run this additional liner into the cavern?
This one, you mean?
This one, exactly. So I assume this, what is this? The 16-inch, the 16-inch casing is probably cemented to surface, right?
That's
And-
cemented to surface, just generic, could be at any depth, just as the formation requires. And basically not all caverns would need such an intermediate casing.
The 1338 also?
Sorry, a
The
1338, I don't
1338
have.
casing or 11.75, is it cemented to surface?
Yes, this is cemented to surface, yes.
So there's no way to monitor this annulus.
This annulus is only monitorable via pressure checks at the surface. Yeah.
Okay.
Yes, my name is Frank Schweitzer. I'm the group manager of the group Lifetime Concepts for Hydrogen Applications at the Fraunhofer Institute for the Mechanics of Materials. And let me just show you 2 slides about this institute. So, but today I'm talking about the mechanical integrity of the hydrogen infrastructure. Mr. Bültemeyer already showed some slides about the components we regarded in the project HYPOS H2 UGS, so underground storage. That's the short version of that. And we I show in the next slides. So Fraunhofer is the biggest organization for applied science in Europe. We have about 30,000 employees, but these are all divided in more than 76. I think it's now 77 or 78 institutes all around Germany. And IWM is directed or located directly at the border of France and Switzerland at the southwest of Germany. So we have a budget of about 3 billion, and this financing is directly related to what we do with industry. So every project we do with industry, we get a bit more financing from the government to go a bit ahead, and that we can offer more applied solutions for industry. Fraunhofer IWM itself, as I said, located at the southwest. We are about 330 employees, and we have an operating budget of about 25 million euro. And in 2022, we had industrial revenues of 25%. So this is quite less because of the COVID situation. This decreased a lot. Normally, we are about 40% with industrial revenues. In my group, just to show 2 pictures, we do a lot of calculations. You see a model of hydrogen distribution in a component or hydrogen component, and we also build up own test systems for hydrogen, but we use some systems which we buy in the market. And our main focus is the lifetime assessment of components. So the motivation in this underground storage systems, and especially in the project HYPOS H2 UGS, is, as Mr. Bültemeyer said, that the material properties for the storage of hydrocarbons and other media was successfully applied for decades. And now we want to switch to hydrogen, and this hydrogen can change the properties of the, especially of the steel materials. So Mr. Bültemeyer showed the packer system. There are also other materials, but we have focused on the steel materials. So as you see on the right side, there's a schematic representation of hydrogen, and you see if there are small or micro cracks forming on the surface, you get stress fields around this, and the hydrogen will diffuse there, and also if it gets to the crack tip, the atoms will separate. There will be a decohesion, or there could be a decohesion. And in the absolute worst case, there could be a fracture, as you see in the picture, in the lower picture. But this is not the only mechanical interaction of hydrogen. So what another motivation is, the standards and guidelines for the safety for hydrogen do not exist yet. So everyone's working around about this, but this will take more time and also a lot of investigations of different materials. And for the H2UGS project, we wanted to try, or we selected a suitable steel and did different types of investigations to see if this fits to the hydrogen caverns. So just shortly, yeah, you all know that. You see the line riser tubes. Just wanted to give this picture. It's not a schematic, so or it's schematic, but you see how long this is. So we talk about a lot of very long pipes. We talk about a lot of stresses acting on these pipes. And in the consortium we selected the pipeline steel X56 as to evaluate, and we characterized it by basic characterizations for steels. We did weld inspections, and you'll see slides of sour gas testing, notch impact testing, so strain rate tensile testing, and we also look at the fatigue behavior, because you have the hydrogen coming in, so you have pressure inside of the tubes, and you have the hydrogen coming out with the release of pressures. So you have cyclic deformation on the steel tubes. And all the material testing were tested by us, Fraunhofer IWM, and by Salzgitter-Mannesmann Forschung, SZMF. I highlighted in the slides what SZMF and what we did. So the first thing we went to the laboratory of SZMF, and we welded the pipes, just that you see what dimensions these have. You see here an arm and a hand of the welder who does the temperature testing. And then we focus on something like that for sound material or bulk material. And for the welds, you see a cross section of the welded pipe here. So it's the root is welded differently than the upper layers. And we did some EBSD measurements of the different weld zones. What you see here, why I show this, is that you see you cannot say I have a steel with a certain microstructure. You will have a welded steel, and you will have also different microstructures in that steel. So the bulk material looks like that. The different zones in the heat affected zone look differently, and the weld, because of the other weld metal, also looks different. So you have to look at all possible microstructures of the component. So at Salzgitter-Mannesmann Forschung, there was sour gas testing, which was very important. So they looked for hydrogen-induced cracking. You put or take out different samples of weld material, of sound material, and you put that into 1 bar H2 to H2S and test that for 4 days. And there could be a pressure buildup due to hydrogen, and then you have blisters. What you see in the lower picture. So you will have blisters. That's for ferritic steels. That's common. So you have an acceptance rate. If this is it has to be below 5%. And what we found in the project for the X56 steel is the detected blisters are a maximum of 0.8%. So this fitted well for the hydrogen caverns. Also, you can you take out samples like this and put them under stress. For example, by 4-bending machine, put this also into a 1 bar H2S partial pressure. Also the same duration or an extended duration, about 30 days. And also you do an optical evaluation, or you can do magnetic particle testing to see if there are cracks building up in the materials. And for the X56 steel, the ferritic steel we investigated, there were no cracks registered in both the weld metal, the base metal and the weld metal for all welds we had. So this was also very good for us. Then when you have the component, you come in contact for sure with hydrogen gas because we fill that into the caverns. Now in the different you have different possibilities to test that. You can pre-charge your steel samples by hydrogen and test them. You can put them in an autoclave system and put hydrogen around this, and you can make a hole on the inner side of the samples and test the hydrogen or the hydrogen mechanical interaction from the inside of the samples. So one case is you see here a slow strain rate tensile test. This is a quite big one in our house. So you have a tensile machine, what you see here, and you have an autoclave system where you can have high pressures of hydrogen gas. You can also cool it or heat it up a bit. And what you have to do, you have to measure these samples at a very low strain rate, that the hydrogen has enough time to diffuse to the crack tip, as I showed in the first picture. So the hydrogen diffuses to the crack tip. You have to do all experiments with hydrogen at a lower rate than in standard cases. In the H2S project, we used or Salzgitter used an inert gas, hydrogen, and a mixture of hydrogen and H2S. And you see the results of a tensile test on the right side. So you tension the sample and measure the stresses, and you see the black line. This is inert gas. Red lines is hydrogen, and gray and blue lines is or gray line is N2 and H2S, and blue lines is hydrogen and H2S. And you see that the material is not able to deform so much the more hydrogen comes inside. And you also see this on the fracture surfaces. On the left, this is inert gas, and you see changes with hydrogen, and you see large changes with H2S. An alternative method is the tubular specimen technology. As I said, you take a standard sample, make a long hole inside of it, and fill it with hydrogen, put it in a tubular fixture, and then what the main advantage is, you can put different things around it, heating chamber or induction heatings, or also cooling to very low temperatures or lower temperatures as you like. So this is a big this really good to handle. Also in the project, we used that to measure the fatigue properties, which is not so easy in these autoclave systems. So also you see here stress strain curves with the hollow samples. You also see the reduction by 100 bar hydrogen, and you can also have a look on your on the fracture surfaces, and you see a change from ambient air with a ductile behavior to a more pronounced fracture surface with hydrogen. So as I said, the main it's these inner bore samples. They are quite good to do also not only straining the material, to do cyclic testing. We especially look here at low cycle fatigue because we don't have very much cycles in the caverns or in the steels for the caverns. And the main advantage is really that you have a very closed system. With a normal autoclave system, there's always the problem that you get single molecules of oxygen inside of the system, and this alter the outcome of the experiments a lot. So what you see here, solid specimens in air is red dotted. Then you have the hollow specimens in air, and you see that this lays together, that you can use solid specimens, hollow specimens. And then we had 50 bars of hydrogen in the X56 steel. And you see that on the x-axis you have the cycles, and on the y-axis you see the straining of the material. This is all at room temperature at a quite low frequency. And yeah, you see you can, yeah, the steel shows a bit changes due to hydrogen. But you can also use this diagram, for example, to calculate or to do your calculations for the mechanical part of your Caverns. You have a lot of influences for the low cycle fatigue, the loads itself, the pressure. The more pressure you put in, the more pronounced is the reduction here. Test frequency is very important. As I said, you need a lot of time for let the hydrogen give enough time to diffuse to the process zone in the steel. Temperature, for sure, is changing the outcomes. And as I said, you always have to test all zones in your material. Then what we also did and do, if you have an hydrogen in your system and you have small micro cracks, there will be the crack propagation will be different in hydrogen than in inert gas, for example. So we really see a strong effect on the crack propagation. This is what you see on the right side. I'm sorry, this is in German. I only have this diagram in German. So what you see here, you have dA, dN. This means dN is one cycle. So you take your sample and pull it one time, and the dA is the crack opening which happens due to that. And the more open the crack gets, the more pronounced comes the stress intensity on the lower side. And you see the normal shape of these curves is, yeah, you see nothing. So this there's no propagation. Then you have a threshold, and then you have a linear relationship with the crack propagation. The crack starts to grow faster and faster, and yeah, at the end of this, there's a catastrophic failure. But you don't see this in this diagram. And what you normally in ferritic steels see here in with hydrogen, that you don't have this linear relationship. You have another an advancement of the crack propagation. So the crack grows much faster with hydrogen than with normal air. This also, yeah.
Yeah, 3 minutes left.
Yeah, okay, that's perfect. Thanks. And also what you see here, blue is sound material, and red is the circumferential weld, and green is a longitudinal weld. So, but this is not our measurement. This is from literature, but it shows it quite well. And you see that the sound material and at least the circumferential welds behave quite the same. Then this is quite different to other experiments, but for the crack propagation, this is an important outcome. So we also did additional tests in the HYPOS UGS project. We did Sharpie tests with preloaded samples, but we were not so satisfied with the results. I think there has to be more work to do with that. So the main problem is with ferritic steels that the hydrogen gases out in short times. And also, we measured the critical stress intensity, but for the X56 steel, we could just say the steel is too ductile for this type of measurements. And this is good for the Caverns. This means you don't have a real critical stress intensity or an enhanced stress intensity with hydrogen. But the result is not, you cannot really show this because it's if you use the standards, it's not inside of the standards. So the main outcomes of the project was for the investigated X56 steel tube, the main influence, really the main influence appears to be the hydrogen sulfide. So we always have to look for the H2S contents. If you have only pure hydrogen and no H2S, there's a minor effect expected when the pipe is operated below the yield strength. Above yield strength, you get micro cracks, and as I showed, the hydrogen will pronounce the crack propagation. And we tested, as you saw, the influence of hydrogen sulfide with mixed gases and with nitrogen and with hydrogen. So this means not the hydrogen gas and H2S mixture is not relevant for the crack propagation. So the hydrogen, the H2S together with moisture is the most thing you have to look for. And one smaller outcome is if you only have hydrogen, you can do a lifetime consideration with the curves I showed you. For example, at this time, you use the well-known ESME B3112, but always keep in mind that it's not specifically designed for Cavern in the riser tubes. So thank you for your for your attention, and this was a short overview. I'm open to questions, to every single investigation, and if you have more complex questions, please don't hesitate to contact me.
Yeah, thank you very much. And it's always good to hear that moisture is the problem to almost everything.
Yeah.
Well, we do have one question in the Q&A section. Do the stress tests also account for significantly different operating patterns of storage input from dynamic hydrogen generation due to fluctuating RE feed-in patterns?
So if I understand that correctly, that is what I wanted to show with the LCF. So we got data from the partners which show how much pressure gets inside of the system over the month and years, or maybe let's say over 1 year. So we know how many cycles we have. So there will in most times it was said that the cavern is not going to zero with the pressure. It's just you put something in, you take hydrogen out, but not the whole hydrogen of the cavern. So, but you know how many cycles you have per year, and you can take these steel examinations or these curves I showed you to investigate how thick your component has to be.
I thank you very much. And I would go straight to Jörg Fröbe. He will tell us basically about the surface facilities when it comes to operational aspects and permitting.
Thank you for the introduction. I want to talk about what is above hydrogen caverns. That means the development of surface facilities for hydrogen, which was included as a part of the H2 UGS project of HYPOS complex. And okay. And the agenda for this presentation would be some items, short introduction of ESK, the above ground facilities for cavern storages we have developed in the project, hydrogen as storage inventory. That means consequences for planning and operations, the purification requirements, but this did Hagen Bildemeyer always refer. Approval process and outlook and relevant projects in a short sketch. Yes, ESK is since 1991 on the market, and we are almost in Europe, but also all over the world in some projects included. And we are the main aspect of our work is subsurface, but surface facilities consist also or belong also to the storage. And yes, from the qualification, our engineers are all engineers, petroleum engineers, geoscientists, geologists, and scientists, and drilling engineers. And the following charts shall only give a raw overview, and you can read it if the presentation is available for all. Yes, we do engineering and underground storage facilities, and from repair to owner's engineering, we provide services. We have software products that the newest, maybe it's known, is Boris Cloud for well integrity studies of wells as a subsurface matters. We have also CavPool and PoreTech, which is a thermodynamic simulator for gas caverns and material balance for porous rock, like aquifers and so on. Also consulting services and surveys. We do conceptual studies, due diligence reports, and so on. And also we deal with the decommissioning of natural gas storage facilities, surface and subsurface. We did it from the engineering until now for the storage in Buchholz today. The last activities are taking place. Yes, and research and development, first of all, HYPOS is clear, H2 UGS, but also we were involved in Adele. That was a project, R&D project for compressed air storage and adiabatic air storage. Yeah, also conversion of natural gas, hydrogen storages. Also, it's interesting part is the connection to the electrical power storage or electrical teams like redispatch or sector coupling. This only as a short overview. We have also a branch near Dortmund, and they deal actually with the conversion of the gas grids from L quality to H quality. And also for the future, they are beginning now also with hydrogen works. The first hydrogen little network was there in operation. But this is a thing from for literature. Okay, our participation as a hydrogen HYPOS project. We did the design and modeling of surface facilities, the risk identification with operational safety analysis, the analysis of green hydrogen scenarios and model approval process, and a model approval process in direction to authorities. We did it with the input and interfaces with our project partners of this project, but it's only an overview. Yes, that are some bullet points, what our content of work. That means market requirements. We had to research at the first step. That mean working gas maximum rates, but typical cycle lengths for storage, and so purity requirements also mentioned, and so on. We made a little basic design for surface facilities with respect to these market options, component specifications for description of components of the surface facilities. And then we did simulations of the designed variants of the plant. And in the other work package also we dealt with the identification of hydrogen-specific risks, also evaluation of these potentials and causalities, and recommendations also for risk prevention. We did develop exemplary operational control and surveillance regimes, and from in the case or in the line to the authority, we outlined an exemplary approval process. Yes, and the aim for all of these involved companies in this H2 UGS project was the development of a general guideline. Yes, above the caverns, it's a sketch here. You have the caverns in the subsurface, and at the surface may be seen the surface facilities. This is yes, a view from our calculation model, what we have used, and you find the filters, the metering, the compression cooling or after cooling, the field piping, the cavern, and for the production line, then also the purification and pressure reduction, as well as the metering. That's the main points of a surface facility in a very quick and dirty view. Market requirements. We did an analysis of the scientific publications until 2019. That was the starting of the project, and it was under development, it's clear. And you see here the several sources we have evaluated, and we have also our government strategy, the Nationale Wasserstoffstrategie, which is shown here in this line or here. And so what the question, what's the volume of the future hydrogen market with respect of the several kinds of hydrogen? You know the colors, blue, green, gray, and other. And that was the extended market volume, what we could see by the figures. And on the other side, the capacities for production of green hydrogen, what is a significant fraction of expected electricity production. But these figures are under development now, and they are, if you see the timeline, we have closed this project in 22. So today we have actual figures and other deviating points also. Yes, the storage works according to a load curve almost, and we did develop 3 different storage variants with load curves. So we had the variant of start and reference and maximum, and the load curves is for the start variant a weekly curve, and for the reference and maximum an yearly curve. And so we did also several simulation runs with our software tool, CAVT, and with variation of pressure, temperature, and flow. And so, yeah, a lot of simulation to get an idea of the pressure line of the cavern around the year or around the week. So we have stronger, as the expectation for the operation of hydrogen storages is then we have stronger fluctuations than for natural gas storages. And here we have a superposition of small and short-term fluctuations and a large-term fluctuation. That was the situation. We had to have an start point for our simulation or for the layout also of the storages, and that's a starting assumption. Yes, at the end I give a picture of the whole storage layout, but also surface plants layout. We have here as an example the compressor design, which we would take as a base for these three scenarios. We have minimum reference and maximal variant, as you have learned. And in this case, it's a very simple. We would use one compressor. It's a piston type, almost between 2,000 and 5,000 normal cubic meters, with a pressure range on the suction side from 30 to 60 bars. It depends from the pipeline, and the discharge pressure is from the 40 to 140 bars. It depends from the cavern, from the depth, from the from the caverns values. For the next stage, there is a growing. You see, we have between 20 and 50,000 normal cubic meters for the filling of the caverns, and as at the same suction pressure, but the discharge pressure is higher than from 40 to 170. It's nearly the cavern in Lauchstädt, I think, and the maximum variant, we have same suction, but here up to 230 bars in a maximum pressure. And the biggest compressor, it's not the almost biggest, but in the available biggest this time, it was around 100,000 normal cubic meters from 30 to 230 bars at the design point. So, but in this maximum variant, it's the whole cavern volume would cause 10 times such a compressor we would need. So we have to think about other, maybe a turbo type, but this is then the detail engineering task, and in this way, it's, or in this case, in this project, we did only a first poor assumption of this. Here you see the typical design of the maximum variant of this storage, where we have to consider the compressors or the production line. Here is only two lines. In real it would be for redundancy, and so also more lines in parallel. Here you have the pipeline where the hydrogen is available. Then you have the entrance to the storage, the cleaning. You have to remove dust, droplets or water, and if there is some oxygen, you have to remove also the oxygen by a catalytic deoxidation if necessary. So you have to have a cooling and also a droplet separator. Then you have a header for switching to the different or to the boat, in this case boat flow measuring devices for fiscal metering or contractual matters. Then you have the suction header of the or the general header of the storage, so you can switch between the production as the filling lines or the production lines. It's for operational reasons, and in this case, two compressor lines with two-stage with inter or after cooling compressors. Then the manifold header with the field lines, which are connecting each cavern to the surface facilities. And in the opposite direction, when we produce hydrogen, you have these caverns, the field line, and then the line for the production, which consists in a fluid separator with a safety valve equipment. Then you have the pressure regulating string or pressure regulating valve. You have to have the pressure at the end from the pipeline. And then Hagen Bödemeyer said this again before, the cleaning absorption or adsorption for the specific demands of the impurities and the demands at the pipeline.
Jörg, there are 3 minutes left.
Okay, so I have to fast up. That are the differences between natural gas and hydrogen. You see some main differences in calorific value and in critical ignition energy, and also in the explosion limits that you can read after. The purification demands, here you find again the the rules which Hagen Bödemeyer also mentioned. I go through this chart. And then the safety aspects I have to mention. You have this flammability, molecular properties you have to consider. The heat capacity is different, has a different pressure response if you heat input, if you have a heat input into a shut-in volume. And the advantage of hydrogen, you have no hydrate formation in consideration to the natural gas. So the tool sets for the safety we can use from the natural gas, but we have to consider the differences, and that is the difference in this case to the values of hydrogen. Approval process, you know, it is obliged to make this by Bundesberggesetz, the German mining law, and you have 3 stages almost of operation plans: Rahmenbetriebsplan, Hauptbetriebsplan, Sonderbetriebsplan, with increasing detailed description. And then if it is if it fits to the authority, you can get an approval. And recommended is for a waterproof approval is a framework operations plan, Planfeststellungsverfahren, and you have to do environmental impact assessment. Also, it's a Umweltverträglichkeitsprüfung, and this is just in time under construction. There is a draft for the equality of hydrogen to natural gas under work. So I think I have it. Outlook and ongoing projects. You see here some named projects in several countries which are ongoing. Some we are involved, some that are the stakeholders of the projects. We are also involved in ongoing projects, but we have confidential agreements, so that I can't show this here at this place. So I hope it wasn't too fast at the end. Thank you for the attention. My colleague Maurice Schlichtenmeier has holidays today, but he is also, if you have questions, the contact. And if there are questions, please tell me now.
Thank you very much. We do have 8 questions, all from the same person. I would suggest Christian Machens. Could you please turn on the microphone and ask 2 of these questions? Because I don't think all of them are related to the presentation we just heard.
Yes, hello.
Hello.
Can you hear me?
Yeah.
Yes.
Okay. Yeah, I think the question should be related to the surface installation and the operation of these units. I think one question which could refer to that is how much losses will you have from the purification of the released hydrogen in order to meet the high purity requirements? So what are the losses when you are cleaning the hydrogen? Is there waste of gas? Is there purge hydrogen gas from?
I understand. It depends, like always. We have two aspects in this way. You have sure you have losses by purging of something and so on, but from the safety concept of such a hydrogen storage, there is I name it now zero tolerance for losses to the atmosphere. That means in every case you have to gather the hydrogen which is lost from the process, and you have to take it to the flare or so. It is not allowed, or not the philosophy, to take the or give the hydrogen to the atmosphere. And so the losses are to the environment are nearly zero, but losses in the process you can handle by injection of and at the lower pressure stage also, that you could do. But
Okay,
I can't give you a figure or a absolute number of losses. For it depends from the cleaning processes, adsorption and so on.
Okay, you just said it's not allowed to vent hydrogen. Who says that it's not allowed?
No, not allowed, but for safety reasons. If you give the pure hydrogen to the atmosphere, you get an hazard of explosion, which is caused by the explosion borders from 4 to 80% volume percent. You have a higher risk, and this is under discussion today. But it's not the philosophy to vent this to the atmosphere and not to combust.
Okay, I see. So you cannot say how much hydrogen is lost from the cleaning process. Is it 1%? Is it 5%? Is it 0.001%? So
0.0, I think not. But yeah, you have to go to the providers of the adsorption or plants.
Maybe one more question from my side, and I will
yes.
I will have other people also give the chance. The condensate, you have been talking about drying the hydrogen when you release the hydrogen before you feed it into the pipeline. You have to dry it.
Yeah.
What about the wastewater which is produced there, the condensate, I would call it? Can it simply be fed to the sewage system, to the public wastewater system, or because I assume there's a lot of salt and it has a different pH value and maybe some other chemicals contained. So what about that water, the condensate?
Yeah. The water which we get with the hydrogen at the production process from the cavern is in the highest level saturated, the hydrogen, and the water is nearly the same like as at a natural gas storage. And it's a long discussion. I've tried to shorten it, but if you have let's say at the wellhead you have 40 degrees, and they cool down to, let's say, earth temperature. In any case, you have a range of 30 degrees for the dew point reduction, and so you have a theoretical water content. It depends from the cavern what is produced on water with the hydrogen, and this is the amount you have to consider the water. And the history of the cavern construction, you have maybe you have a blanket heavy oil, or you have other hydrocarbons from the history of the cavern. Maybe it's a former gas cavern. And so you have to consider these compounds, and you can say then the water is to treat, or but not to deposit in a river also. You almost in storages you need a special treatment for the water, or a service for this.
What do you think about giving your further questions to the last or upcoming speakers directly, and we will answer them via email?
Yes.
Then we go straight to our next speaker. Mort Ambro is a professor at the Technical University of Freiberg, and he will tell us about methods for leakage assessment and feasibility of CO2 as a cushion gas in the hydrogen storage in caverns.
Thank you very much. Indeed, I will present here two different, not different topics, but two topics. The first one dealing with the integrity of the wells. This is an experimental investigation. What we have done in frame of the HYPOS project. That means we have investigated the well integrity dealing with the cement, with casing cement and cement and formation. And I will move to the next topic, which we investigated also. It is carbon dioxide, CO2, as a cushion gas in hydrogen storage, in caverns. And this is a feasibility study. With me, I have Dr. Freze, Tawfiq Nazan, and Hakan Alkan. Both colleagues here, Tawfiq Nazan and Hakan Alkan, they have good experience on simulation, mainly CMG. I will introduce the results later. So, but before I start, I would like just to introduce our university. Now, the Technical University Bergakademie Freiberg has been founded in 1765, and it's one of the oldest universities around the world dealing with mining and geosciences. Yeah. And I have a problem with that. Now it works, I hope. And we have a clear profile within our university. This is geosciences, materials, energy, and environment. We have a very good connection with the industry and, of course, with the government institutions, and we have a lot of external funds and projects. I will start with the well integrity. As mentioned, we investigated the well integrity in the frame of HYPOS project, and dealing, of course, with salt caverns. And if you look at the definitions of the well integrity issues, or well integrity, all standards around the world, they deal or they define the well integrity as same or similar. But at the end, we will have the same meaning. The meaning is we have to reduce or we have to prevent any uncontrolled release of formation fluids. So we have to. That means we have to prevent any release of fluid or gases or whatever from the location in which we consider as a storage. Yeah. And in addition, we think, or we mentioned that here, responsible integrity consideration are essential to maintain public acceptance of storage project. This is additional definition or additional point for the well integrity, public acceptance. Now, what are the main points we have to investigate to make sure that the well is secure and there is no integrity issues on something like that? We have to deal with the completion, of course, like Parker, for example, safety, subsurface safety valve, and so on. Contact areas with cement. Cement is an artificial material. It's not naturally there. So we have to make sure that the cement is also tight. This is very important. And we have to identify the potential weak spots within the well in general. And we have to eliminate any leakages or any uncontrolled flow in all the components of the system. Of course, cement plug in abandoned wells, it's important. We have to make sure that they are tight. Caprock is very important point. I will share with you some of the results. And we have to enhance the storage capacity. This is an economical issue. How to enhance storage capacity of storage location? We have to consider the threshold pressure of the caprock, mainly. Threshold pressure. This is very important point. So we can investigate such points or such issues in our institute. Here, this is the well integrity schematically. So we have primary barrier. Here you can see the green dashed line, and we have a secondary. We dealt in our institute. We dealt with the primary, of course, with the primary. And when you deal with the primary, we have a critical point in the well, which is the casing shoe here. The last cemented casing shoe is the most important point in the well, regardless if it's cavern or porous media. And this casing shoe, this point, is exposed to high pressure, and there is a link between cement and casing at this point, and cement and formation. Yeah. And we have to consider all these materials exposed to the gas. In this case, is hydrogen. Yeah? And I tried to make it here schematically. We have the casing here, we have the cement, then we have to investigate the interface between casing and cement, and the cement itself. And we have to consider also the cement and salt in this particular case, because we deal with salt caverns, and we have to consider the salt formation itself. That means we have to see the applicability of the salt for hydrogen. So if we want to deal with the leakage or with the flow within the system, that means we have to identify the permeability, which is very important. But we deal with very tight systems. That means we have to identify, or we have to consider certain method to come up with the results as fast as possible. If we consider steady state method, we will take a lot of time to get one measurement. For example, maybe 6 weeks or more than that, just to get one measurement of permeability. We decided to consider the unsteady state, which is time, is a function of time. And within this method, we can identify very small flow rate and very small changes in the system. What is the system? This system we have developed here in Freiberg. We call it two-chamber method. We have two chambers here. I see this is written in German, but it's no problem. We have here the inlet chamber with high pressure, and we have the outlet chamber with very low pressure. And we have the core holder, so-called, and the high pressure chamber is connected with the sample, and the low pressure is connected with the outlet. And we can see any pressure differences or any pressure drop in this one. And when the pressure drop occurs here, the pressure should increase on the other side. When we have an increase, that means when we have increase here, when we have decrease and increase here, that means we have a communication among our core sample. We can identify the permeability. We have a suitable analytical and numerical method. We have developed that in our institute to identify the permeability. We can identify a permeability up to 10 minus 23 square meter, which is close to nanodarcy, lower than nanodarcy. So the pressure and flow rate change over the time can be recorded, and we can use different types of samples, not only salt. We can use, of course, cement and so on. And we investigated a lot of samples mainly for Europe countries here. So again, this is the system I introduced to you schematically. Within this system, we can measure small samples. Small samples, it means in a diameter of 100 millimeter. For example, here such cores. You have here 100 millimeter in diameter. We can measure up to 200 millimeters. This is one of the samples we have measured here. But also we can consider the composite samples, that means cement and casing. In this case is coil tubing because it's small sample, is related to this equipment. But we can use also casing, real casing samples, and we can go up to 300 millimeter in diameter. Oh, I don't have a sample here, it's too heavy, I cannot show. Anyway, and we can use a reactor. Here is a reactor, big scale reactor, and we have the same system. So we can identify or we can vary any parameters you wish. For example, you give us the pressure, confining pressure, or the depth of the caverns, the gas you will consider, and so on, and the samples. Here we have salt sample, for example, we have caprock, anhydrite, and we have cement. And we can identify the permeability. This is only one example, gas permeability at different effective pressure or at different confining pressure. And you can see the higher the confining pressure, the lower is the permeability. So that means we can evaluate the tightness of the sample, and we can also make recommendations to deal with the system if leakage has been detected or something like that, based on our measurement and based on the equipment. Now I will move to another topic, which is carbon dioxide as a cation gas. We investigated this topic, but I mean, this was a small project first, and we had to consider in the project, we had to study the steady state or stationary conditions. That means we consider CO2 in the bottom of the salt caverns, hydrogen at the top, and we had to consider, or we had to investigate the mixture of both gases at a certain depth without injection or movement or something like that. Yeah? So if we consider both gases, CO2 here and hydrogen, if we consider the phase diagram, you will find a lot of differences between both gases. Here, for example, when we consider such operation conditions here within this range, so you will have CO2 in all different status. It depends on the pressure and temperature, of course. We can have it as a gas phase, we can have it as a liquid or supercritical gas, gas, liquid, and supercritical. While hydrogen will have same status, which is gas. This is important. I mean, we know this. And if you look at the density of the CO2, density versus pressure, and consider it or compare it with hydrogen, for example, you can see based on the phase changes in the CO2, you will have kind of changes in the density, which is positive in our case. Positive, it means that density differences between both gases will increase with increased pressure. Okay, good. What we have done, we have simulated. That means we investigated this issue, this mixture issues between CO2 and hydrogen based on the software CMG. Yeah. Here is again the conditions. We consider that the border or the interface between CO2 and hydrogen is at this depth. So we consider the real cavern. Yeah. And the CO2 is in the bottom, hydrogen is in the top. And we have found, or we investigated the mixture or mixing areas in this area of the interface. Yeah. Again, this is the same what I explained before, the schematic of the cavern, and the red line is the center of the cavern. And we can see here, for example, the mixing. Unfortunately, the diagram is not clear, but we couldn't increase the resolution. But we have considered different times, started by 0. 0, it means this is the line. That means you have CO2 at the bottom, hydrogen at the top. And then we increase the time, 100 days up to 1,000 days. And we found out even by 1,000 days that the mixing zone will not be higher than 20 meters. Yeah, but 1,000 day we don't have. So I mean, we have to consider maybe 200 days or something like that. In that time, the mixing zone will be around maybe 5 meters or something like that. But please don't forget, this is static conditions. Now, if we if we decrease the pressure here, this was done by a pressure of 200 bar. So if we decrease the pressure up to 80 bars, the mixing zone will increase. Yeah,
there are 2 minutes left.
Yeah. This is again the presentation or the illustration of the same thing which I showed you. 0, 100, 500, and 1,000 at 200 bars, and you can see the mixing zone, and this is by 80 bars. What we have done also, we did also a CMG simulation for a reservoir for the diffusion between CO2 and hydrogen, and we consider also the microbial and chemical reaction in the porous media. In this case, we assumed, that means there was no project or something like that. We assumed depleted gas reservoir. Then we applied enhanced gas recovery, and then we switched to underground hydrogen storage. So, and we investigated the growth of microorganisms within the porous media. That means we are able, with our infrastructures, to study such issues. So anyway, I will conclude CO2 has been investigated as a cashing gas. I will not go of the integrity issues because I mentioned all the factors. CO2 can be used as a cashing gas under static conditions. I mean, we have investigated that, and we are sure that CO2 can be used as a cashing gas in hydrogen storage. The phase behavior is very important. We can model it by CMG. The economic feasibility using CO2 as a cashing gas, especially in porous media, is very important because at the end of the day, you will have finally a CO2 storage location. That means if you stop the using hydrogen or something like that, the chemical and microbiological reactions can also be modeled. In the case of higher uncertainties, so we have to consider a lot of parameters and we have to do a lot of investigations to consider all uncertainties and to study the effect of them. Thank you very much. This is the last slide I have. Yes.
Yeah, we have one more question for you.
Yes, please.
The person who is asking is curious about the mixing zone found. What was the reservoir thickness? I think he's talking about the CO2 mixing zone.
Yeah, but here we considered only cavern. That means there is no mixing zone. I can share with you the slide again. Here we considered only open system, which is cavern. Yeah. As mentioned, we have the salt caverns. We got it from one of the companies, and that was our border or our interface between hydrogen at the top and CO2 at the bottom. And we found out that that almost 20 meters is the mixing zone. But the question is really very good. We considered porous media in this particular study, but we are not completed. That's the reason why I did not show the results of porous media. But in the porous media, you will have higher area of mixing zone. Because you have here conductivity, you have not only convection, but you have the heat conductivity is high in the porous media.
Okay, thank you very much. I hope this answers the question. If not, feel free to write us afterwards, and we will handle further questions to the speaker. Thank you very much. Are there any questions from the audience? I hope you've seen the applause that is given to you.
Thank you.
But I don't see any questions. So, but still, if there are questions coming up after this event today, feel free to contact us. We will send it over to each speaker. Our next speaker will be Daniel Lutman from UGS, and he will tell us something about concepts for new and existing caverns. Hello, and please start. Thank you.
All right. Okay. So welcome to a quick run through possible completion designs for hydrogen caverns. At this point, I only will go superficially through the topic, but I hope everyone can follow me as well. To introduce myself, my name is Daniel Lutman. Currently, I'm the head of the Department for Cavern Completion and Testing at UGS, and I'm working for now 14 years at UGS. Okay, let's get right into the topic. In terms of order, I will go into the current status again in the presentation, then move into special requirements for hydrogen, and conclude with possible completion designs. Well, in general, we have a wide range of cavern sizes, depths, and shapes, and depending on this, the pressure, temperature, and flow rates also vary. In principle, there's a large amount of practical experience in the industry in dealing with oil and gas storages. The planning processes and design principles are also very well known. The caverns in particular have practical advantages as a storage for hydrogen. So hydrogen does not react with the salt as surrounding rock. It can be stored and retrieved at a short notice, and provided you have a cavern filled with brine, a partial fill would also be possible. However, there are also challenges to overcome. Unfortunately, there is no or very little experience about the reactivity of hydrogen with the materials used in the well. For example, the metals, cement, or the elastomers from downhill equipment. Furthermore, the history of the cavern must be taken into account when using the cavern as a hydrogen storage to avoid negative influences. For example, during the leaching process, wastewater has been used. Okay. In Germany, we are using the industry regulations of the BWEG as a guideline to design of a well completion. You have heard that on presentation before, so I keep it short. We use two barriers. The primary barrier is the one that has direct contact with the storage medium, and the secondary as a fallback option. So the primary barrier is a production string, and the secondary barrier, the production casing. And before we put the system into operation, an integrity test must be carried out. And clearly a safety valve has also been in there. The picture you've also already seen. The blue one is the primary barrier. The red one is the secondary barrier. Well, if you look at the barriers, we quickly arrive at the resistance to the storage medium. Compared to natural gas and oil, hydrogen demands special requirements of the material. In case of steel, attention must be paid to the chemical combination with a fine-grained structure, regard to embrittlement, tensile strength, and hardness must also be limited. Furthermore, a minimum notched impact strength must be applied. A material approval for an API J55 is available in principle, but in this context, it must be said again that the specification of the API for a J55 is not sufficient. While the effect of hydrogen on steel was explained in more detail in the presentation by the Fraunhofer Institute, so keep it here short. And further material approvals are in progress right now. The verification of the suitability of the elastomers and the cement is still outstanding. However, there are cement suppliers who have tested the cement in the laboratory and are also promoting it. In general, with regard to the casings to be installed, welding is preferred to a threaded connection. Well, now let's move on to possible completion designs. At this point, it makes sense to divide into two categories. We have the existing caverns, which can possibly be converted, and newly constructed wells. For existing caverns, usually the installed material does not meet the requirements for hydrogen. This can start with the steel of the casing and strings, move over the elastomers from the pucker, and possibly to the threaded connections, depending how the casing or string is installed. One option here would be to cover the existing completion with a new hydrogen suitable completion, combined with an adequate leakage test. Unfortunately, this option brings with it, for example, a significantly reduced inter diameter, which also causes a limited flow rate when you move the gas in and out. If it's not practical to cover the old completion, for example, because the casing shoe is leaking, the production casing could be partially milled, and the new casing with also a new casing shoe could be installed. In the drawing here, this is a double string completion, combining the production casing and the production string. The pucker here is replaced by a double string shoe. The great advantage of this system is the larger internal diameter. And by the way, the double string shoe is a custom development by UGS. Well, finally, the selection of the completion design depends on the general conditions such as measurements, test results, whatever you can find for the old well. For new caverns to be completed, the completion design can be based on the current standard for gas caverns, which means you use a combination of pucker, production string, and safety valve. The individual components are then to be adapted to the special requirements for hydrogen, which brings us back to the challenges mentioned above, the material selection for steel, elastomer, and so on. And here the standards and certifications are still missing. So the basic design isn't different from a natural gas completion, and it's finally more a question of the material selection. So that was a real quick run. At the end, a few words on behalf of UGS. Without reading out the content on the slide, I would like to mention that UGS as a service provider can accompany and handle the complete spectrum of a storage facility from a single provider. We have engineering for surface, subsurface, and can be there from the first steps through to realization. We also have an drilling and workover rigs and can also manage the operation of a storage facility on site and remotely. Yeah, that's it. Thank you for your attention. And if there are any comments or questions, you're welcome.
Today, I think you, Petra, are biologists, and we are happy to hear why also biologists deal with salt caverns. Yeah, we can see your slides. Yeah, you can start.
Okay, thank you very much. Yeah, I welcome everybody to my presentation. My name is Petra Bombach and I'm scientific assistant at the Isodetect company, and today I and Martin Wagner from the MicroPro company want to give you a presentation about the microbial impact on hydrogen storage in salt caverns. So let me briefly introduce the Isodetect company. So we were founded in 2004, and we are a spin-off company of the Helmholtz Center for Environmental Research in Leipzig and of the Helmholtz Center in Munich. What we do is we provide microbial examinations and compound-specific stable isotope analysis to elucidate the biological and also geochemical processes in underground gas reservoirs and at contaminated sites. Why to investigate microbial processes in salt caverns? So hydrogen is an excellent chemical energy carrier, but it's also an attractive energy source for a lot of microbes living in salt caverns. So in general, there are 4 different processes which are known that, that microbes can consume the hydrogen. The first process is called the sulfate reduction. So the microbial hydrogen consumption is coupled to the reduction of sulfate under the formation of sulfite. Second process is called the sulfur reduction. So the hydrogen consumption is coupled to the reduction of sulfur, also under the formation of sulfite. A third process is known, which is called methanogenesis. So the hydrogen consumption is coupled to the reduction of carbon dioxide under the formation of methane. And a fourth process where also the hydrogen is consumed, coupled to the reduction of carbon dioxide, leads to the formation of acetate. This process is called the homoacetogenesis. So as you can see, these microbial processes can lead to a loss of the hydrogen and to a pressure decrease. From the technical point of view, the sulfate reduction and sulfur reduction are the most unwanted processes due to the formation of the sulfate, which creates problems on the gas quality and causes souring and corrosion of steel material. So in order to ensure an efficient and economical, successful underground hydrogen storage, the microbial impact on the hydrogen storage should be investigated. This was done in the HYPOS project H2 UKS. It was already mentioned before. So within this project, the microbial analysis was performed in close collaboration of the Isodetect company, of the MicroPro company, and of the Helmholtz Center for Environmental Research. All the results and methods are well documented in a guideline, which you can download from the webpage. I have to mention that the guideline is only available in the German language. In the next slides, I will you explain methods how to assess the microbial aspects on the hydrogen storage and show you the most important results of this research project. So if you are in the planning phase of a salt cavern hydrogen storage, there are different relevant parameters and methods to assess the microbial risk on hydrogen storage. The first one, I always recommend to perform hydrochemical analysis. Microbial activities are influenced by the hydrochemical conditions present in the salt cavern. All microbes require for their growth an energy source, which can be the hydrogen, and an electron acceptor for energy generation, which can be, for example, the sulfate. In addition, the microbes require trace elements such as nitrogen or phosphorus, and a carbon source for the microbial growth, which can be carbon dioxide. So based on the hydrochemical information, we can already see if microbial growth is possible and which microbial processes might occur. A second method is based on molecular analysis. So what you are doing, you extract all the genetic information of the present microbial communities in form of DNA. And then you can later analyze the DNA by sequencing or polymerase chain reaction analysis in order to quantify and characterize the present bacteria, archaea, sulfate reducers, and methanogens. Another method are laboratory studies. So you simulate a hydrogen storage in the laboratory. You take your microorganisms, which are in the salt caverns, and bring them in contact with hydrogen. And then you can analyze if these microbes degrade the hydrogen, and if yes, which processes are occurring and how fast are these processes. And a fourth method, it's called the compound-specific stable isotope analysis. I will explain you the method a little bit later. So coming to our research project, within the H2 UGS project, 5 different caverns in Bad Lauchstädt were sampled. And in all the 5 caverns, we found, based on microscopic analysis, microorganisms with an abundance of 10 to 7 million cells per milliliter, which is quite high. From all of the samples, we isolated the DNA and sequenced later the DNA in order to figure out which microbes are living there. We sampled 2 caverns, which were used in the past for the town gas storage and later used for the natural gas storage. And 3 caverns were sampled, which were always used for the storage of natural gas. For each sample, duplicate analysis was performed. So this is always given in the number 1 and 2. These are always the duplicates. And you see for the duplicates, with exception of the cavern B, the community compositions are quite similar to each other. I would like to draw your attention to the composition. So what you can see is that each of these caverns has a really unique microbial community composition, which has an influence on the microbial processes which are occurring. So all of the caverns are located quite close to each other, but each of them has a high variability of microbial community. So next, what we did, we wanted to know if these microbes also consume the hydrogen. This was done in laboratory studies. Martin Wagner will explain this later. Maybe one sentence to this, we could see that the hydrogen is consumed by some of these microbial communities. And according to these results, we were looking for tools how we can later, during the underground hydrogen storage, monitoring these microbial hydrogen consuming processes. If we have a look to the biological relevant molecules, which are the hydrogen, the carbon dioxide, the sulfate, and the methane, all of these molecules consist of the elements carbon, hydrogen, oxygen, or sulfur. And you find these elements in the nature in different stable isotopes. So, for example, the carbon has 2 different stable isotopes, one with the mass of 12, this is the light isotope, and you find it in the nature with an abundance of 98.9%. And the heavy isotope with a mass of 13, you find it in the nature with an abundance of 1.1%. This isotope ratio, so the ratio of the heavy to the light isotope, can be measured by an instrument which is called gas chromatography isotope ratio mass spectrometry. And you don't measure the total ratio of the heavy to the light isotope in a sample, but always this ratio of the sample compared to the heavy to the light isotope of an international standard. All these isotope values are given in per mil. Why to use this method? It is known that microbial processes often leads to a change in this natural stable isotope composition. So it's a tool how you can trace the microbial hydrogen consuming processes. To give you an example, we did a lab experiment with microorganisms which are able to degrade the hydrogen under the formation of methane. What you can see in the diagram is on the x-axis you have the incubation time, and on the y-axis you have the isotope composition, the so-called delta value for the hydrogen. In gray we have a control experiment where the microbial activity is inhibited. So we don't see any change in the isotope composition. in contrary to this, in the living cultures, we see a strong shift in the isotope composition, which is caused by the microbial consumption of the hydrogen. This effect could be also observed for the carbon isotope composition of carbon dioxide and also for methane. So according to the results, the microbial processes can have an impact on the hydrogen underground storage. Therefore, we recommend to monitor such processes during the hydrogen underground storage, and we developed a concept to monitor such processes in situ. So we recommend to analyze regularly the gas composition in order to see if there are already some changes. And as I showed you, the hydrogen stable isotope composition of hydrogen can be used to provide evidence of microbial hydrogen consumption. This method was already applied at a field site where hydrogen was injected. Based on molecular analysis, you can see changes in the quantity and also in the microbial community composition during the underground hydrogen storage. If there is evidence of microbial hydrogen consumption, stable isotope analysis of sulfate and methane can be performed in order to see if the hydrogen consumption is maybe coupled to the sulfate reduction or methanogenesis. And
Petra, there are 3 minutes left.
Yes, thank you very much. And in addition, in laboratory, microcosm biocides can be tested, which will Martin Wagner explain afterwards. So this brings me to the end of my presentation. Thank you very much for your attention. And if you have any question or you need support with microbial analysis, just let me know.
Okay. And there's a question to Petra Bombach. Is there a possibility to insert material into a well that could filter that microbes out of the gas or water stream?
I think this is a quite challenging issue. So there is no system known for this.
Thank you, Mrs. Bombach. Thanks for the answer. I wasn't sure whether or not something in this direction already was under development, that you pull in what, I don't know, some kind of spongy material or something that might then pick up the microbes during the operation of the gas storage, for example. But yeah, just curiosity. Thanks.
I think there was in the Netherlands was a research project trying this, but I have no detailed information on this.
I think, yeah, I remember that was something together with Uni Wageningen and Shell. Yeah,
yes,
I remember
yes.
that. But they built in some kind of, I think they built in rock material.
A kind of packer or something like this. Yes.
True. Yeah. Thank you.
I would suggest Martin Wagner is continuing because it's a similar topic, and then we will see what the questions will look like.
Good afternoon. I will explain our part of this in this project. I keep it very short and do not want to delay the lunch as much as possible. So my name is Martin Wagner. I'm the head and owner of MicroPro. We were part of this project as a microbiological laboratory. I give you some keynotes about the company later. First, just change here to the next slide. Yeah, what was our contribution to this project? As Petra Bombach already told you, we did some microbiological investigations on the original and samples from Caverns. This is part of our general service we provide to the industry. So we characterized the microbial populations in the brine samples from the caverns and some above ground installations. We determined the microbial hydrogen consumption and conversion rates to the different pathways already mentioned. So, for instance, the methanogenesis or sulfate reduction. We did risk assessment and of the microbial stimulation by hydrogen, and together we defined the low risk conditions and proposed this monitoring program to help the operators to keep the storage clean and properly working. Further, we did some investigations to study potential measures to suppress microbial activities in this type of underground storage. We could easily detect microorganisms in almost all samples from the caverns, which was not that surprising, as we know that there's almost all caverns and underground storages are contaminated with microorganisms. We detected these different types of microorganisms also in these samples from caverns, subverters, and even in very new caverns in solution. So I would briefly explain some of our work packages. So we first enriched the bacteria of different types of bacteria on selective nutrient media. So we cultivated the original bacteria from the samples and did microscopic analysis of these samples with different types of microscopes. And we also did chemical analysis of the original samples and also of the samples from the cultivation tests, of course. With the selective cultivation of site-relevant microorganisms, we could distinguish between different groups of microorganisms, as mentioned, the methanogens, sulfate reducers, acetogens, or iron reducers, which are the most relevant groups of microorganisms able to degrade the hydrogen under anaerobic conditions. Further, we run some consumption tests with hydrogen at slightly increased pressure up to 2 bar in wide ranges. So we could use either the original samples or similar samples from underground sites, from other sites, to compare with originally already cultivated cultures in the lab. So these laboratory studies demonstrated that microbial hydrogen consumption was possible, mainly combined with the sulfate reduction process, which is, as already mentioned, the most relevant process due to the production of H2S. Further, we had a program to run high pressure simulation tests with hydrogen. We are able to use high pressure units to simulate the original and real reservoir conditions up to 180 bar and high temperatures. So we can simulate the real site conditions, temperature, original fluids were used, and also cuttings from the rock, and of course different types of gas composition. These can be modified, and the tests run for several weeks and up to 3 months. So we were able to detect any changes in the gas composition due to the microbial activity during the test phase. This is combined, of course, with the extended data monitoring program to detect the changes in the gas phase and the liquid phase, and also finally potential changes or shifts in the microbial composition of the population. And these high pressure tests also show that it is potentially possible that microorganisms grow and are able to degrade hydrogen under real conditions of the reservoir at the original pressure and temperature. We detected that not the original samples from the reservoir, but comparable compositions and comparable enrichment cultures were able to grow under these conditions. So there is a certain risk of microbial activity also under the conditions of cavern, even in saturated brine. That is the most important point. Based on these data and information from the laboratory tests, we did a risk assessment and to define the growth parameters which enable bacteria to grow and to significantly degrade hydrogen under the reservoir conditions. These risk assessment was also combined with the biocide tests. We have tested several biocides to determine the effective concentration to suppress microorganisms from the growing. So different types of biocides were tested, and we also tested different conditions which might be modified in the reservoir, for instance, pH, to suppress microbial activities. And all these information were included in the monitoring program and also in the recommendations for action to minimize the microbial activities in the reservoir. Or here in this case in Caverns, yeah. Yeah, that's actually a brief overview of what we did in this project. Let me just give you a short some notes about our company. We were established in 1997, and we are a service provider for the industry and research partner for academic partners. We run microbiological, molecular biological analysis of samples from underground sites, reservoirs, storages, caverns, everything which is related to the underground, and also for above ground installations for industry partners worldwide. We are able to run the high pressure simulation tests under real storage conditions, run biocide tests, and do the microbial induced corrosion analysis. We provide or study treatment strategies and have a lot of research about biotechnological processes. Currently, we run a project about the microbial production of hydrogen. So we deal with these classic microbiological issues. Yeah, if there's any questions, you get my contact data here. Thank you for your attention.
Thank you very much. We've got one question for you. The found microorganisms, do they have an influence on the overground technical equipment? For example, compressors, fuel cells, gas turbines, and so on.
Yes, there might be. I can only say it like this. We know that there is a transport of microorganisms of the original cells by the gas phase into separators and above ground installations. That is known. These microorganisms from the underground storage can be transported into filter systems and so on. This is not very relevant for the technical operation. More relevant is the indirect effect of the microorganisms or of their activity due to production of H2S, for instance, or corrosion effects which might be induced by these microorganisms.
Again, if there are any questions coming up within the next couple of hours, next couple of days, feel free to contact us. We will hand these questions over to our speaker today. Finally, I have to say thanks a lot to everyone who was involved today. Thank you very much for telling or for letting us be a part of the knowledge you developed the last 10 years for this specific salt cavern. And it was a long journey to finally get to this stage. I finally want to share my screen. My colleagues told me I should sum up everything, but I think it's too hard to do so. We referred, it's pretty hard to sum up every little detail we referred today. But in general, the message we want to deliver is we do have quite some experience when it comes to this topic, and we want to let you be a part of that. And you've heard a lot of service providers today that can help you if you think yourself of a salt cavern to use that for hydrogen use. Feel free to contact us. And last but not least, I showed you this graphic before. If you are interested being a part of our HYPOS family, also feel free to contact us. You've seen what we can do. Our goal is to let you participate at the knowledge we developed. And the overall common goal is, of course, to increase the hydrogen market ramp up. With this, let's say, little piece of puzzle, which is a salt cavern. We have many other fields of activity when it comes to the market ramp up of green hydrogen, from energy-intensive industries to the chemical industry, to mobility, and so on. So we like to stay in touch with you. And of course, we would always like to improve. So please scan this QR code with your phone to evaluate today's event. We will send you our presentation and the recording afterwards. And we will let you know how the developments at this energy park in Bad Lauchstädt and especially at Cavern are going on. And we would like to contact you for further events of ourselves, and feel free to subscribe to our newsletter. It will let you know all the major facts to the hydrogen market, especially within Germany, but also within Europe. And I would like to invite you. HYPOS is celebrating its 10-year anniversary at the 9th of November in Bad Lauchstädt. And we also provide a field trip to that salt cavern. Not just that cavern, also the wind park, which is under construction now, the electricity transformation facility, and the cavern. So it will be very interesting, and we will have discussions where the hydrogen economy used to be within the last 10 years, and we will look ahead where we will want to be for within the next 10 years. So finally, thank you very much for participating, and I hope to see you next time. Thank you very much.